Alright guys, so we did some regression problems, now it's time to work with classification. And in case you forgot, classification is when we don't have any objects, any values on a sliding scale. We either have something that is something or it isn't something. So in this example, we are going to be taking a look at a data set of breast cancer tumors and determining whether or not they are malignant or benign. So you can imagine this problem is hugely important because it can save lives and help doctors save time as well. So the first thing that we're going to do is we are going to connect to our Colab runtime. And once it's connected, we're going to press upload, and we are going to upload our cancer data set, which is called cancer CSV. All right, now that we have that, let's take a look at our data set. So if we open it up here, you see we have the ID, which is basically, you don't have to worry about that. It doesn't have anything to do with the machine learning that we're going to be doing. And then we have the diagnosis, which is M for malignant or B for benign. And then we have our radius mean, texture mean, and all these other data points about all these other features of a given tumor. And then from that, we are going to try to predict if that tumor is malignant or if it is benign. So let's import our data into Colab. First, we'll say import pandas as PD. And then we will set our data set equal to pd.read_csv. And we will say cancer.csv because that's the name of our file. And then also, remember, we have to split our data into the X and the Y. Now, as you can see, there are a lot of features and I don't feel like counting them all. So I'm just going to print the length of the dataset dot columns. And that will show us that we have 32 columns. So 32 columns, that means 31 indexes, and we don't need the ID index and we don't need the diagnosis because that's going to be our Y variable. So that means that X is going to equal to dataset.iloc, and we're going to have just a colon, and then we're going to go from the second value, 0, 1, 2, which is radius mean, all the way up to the 29th value. And of course, we're going to put dot values at the end of this as well. And then let's also set up our Y variable. Our Y variable is equal to dataset.iloc, and it is just going to be the first column, which is to say the second column, because we have 0 and then 1. And I'll put dot values there. I'll run that. Okay, all is Gucci. So next it's time to do train test split, and it's really important to note that we need a training set and a testing set, even more so for classification problems, because something like misclassifying a tumor can be a matter of life and death. So being able to make sure that our model isn't just overfitting on our data and just understands our data really well, but doesn't understand new data is really, really important. So we're going to say from Scikit-Learn.model_selection, we're going to import our train test split. And then we're going to say the X train, the X test, the Y train, and the Y test are equal to train_test_split, our X and Y. And we are also going to set our test_size equal to 0.2 or 20% of our data, which for 569 entries means that we'll have a little more than 100 entries saved for testing our model. So we'll run that. Looks like all's good. Next, what we're going to be doing is we are going to scale our data. So as you can see, some of these numbers are all over the place. For instance, you have numbers in the hundreds and then numbers in the 0.01s. And if you think of in a graph, if you have one variable, say like the x2 variable, that's super, super big and the other variable isn't, then it's going to be harder to see a correlation. What you want is you want all the variables to have a similar scale so that it's easier to find that correlation, that line of best fit. You basically want to exacerbate the features of the model and how they are related to each other. And so in order to do that, we do scaling. So we're going to say from Scikit-Learn .preprocessing, we're going to import our standard scalar, and then we're going to set scalar equal to standard scalar, and then we are also going to say our xtrain is going to equal to scalar dot fit underscore transform xtrain, and we'll do the same thing with our xtest. And this will basically just ensure that our model can understand the data and doesn't get too confused with the numbers being all over the place. If we put all the numbers on a set scale, it's going to be easier for the model to draw conclusions. So we'll say xtest is equal to scalar.fit transform xtest. Great, so we'll run that. So now that our data is scaled, it's time to do logistic regression. And you might say, hold up, regression was the last section of this course. Shouldn't we be doing something with classification in the name? And I understand that that's confusing, but logistic regression is actually a classification algorithm. And the reason for that is that if you look at the image on the screen, what we're trying to do is we're trying to predict if a tumor is malignant or benign. So if it's 0 or if it's 1. And as you can see here, we can actually use linear regression to solve this problem. However, it doesn't work very well because linear regression is supposed to work on sliding values, right? And obviously a tumor is either malignant or benign. It's never going to be in between. And so because of that, we do logistic regression, which does the same thing as linear regression, but it takes into account the fact that those values in the middle right there, we don't have to account for them. We don't need a straight line. We need a curvy line to show the differences between 0 and 1. And so with that being said, it's time to import our logistic regression model. So we'll say from Scikit-Learn .linear underscore model, we're going to import logistic regression. And then now we are going to set our model equal to logistic underscore classifier. And we'll say logistic classifier is equal to logistic regression, empty parentheses, and then we'll just say logistic classifier dot fit, and we will fit our x train to our y train. All right, so we'll run that. And something that's important to note here is that if you notice, we've been leaving our parentheses blank when we make the model. And that's because we haven't been putting in any hyperparameters. If you see here, these are the default parameters that are assumed when we put nothing in the parentheses here. However, if you want to make your model more and more accurate, it's nice to sort of play around with some of these parameters and see if you can make your model more accurate. Now, luckily, the Scikit-Learn documentation is really good at explaining what each of these different parameters does. So I'm going to leave some links down below so that you can sort of work that out and figure out what each of these parameters mean if your model just isn't as accurate as you want it to be. With that being said, it's now trying to see how accurate our model actually is. So what we're going to do is we are going to set ypreds, and we're going to set our predictions equal to logistic classifier dot predict, and we are going to predict the x-test values. And of course, we have the y-test values as well. So we just show the two, we just compare the two, and we'll be able to see how accurate our model is. And so in order to do that, we're just going to say from Scikit-Learn dot metrics, we are going to import the confusion matrix. And the confusion matrix is hugely important because what it's going to show is it's not just going to show how accurate our model is, but it's going to show how many examples our model misclassifies and what types of misclassification our model is performing. So just to sort of show you what I mean, we're going to print out our confusion matrix, and the confusion matrix parameters are going to be the y-test and of course our y-preds. So let's print out the confusion matrix, and you can see right here you get 2 columns and 2 rows, and basically these 2 data points, the 69 and the 42, represent the number of correct predictions, and these represent the number of false predictions. So what a confusion matrix does is it gives you a little bit more info on what exactly your model is misclassifying and what your model is getting right. So up here, this represents the number of positive values that were predicted to be positive. This represents the number of negative values that were predicted to be negative. So since these numbers are both very high, that means that our model is pretty accurate in that sense. Now, over here, this 1 means that the model predicted that a value was positive, but in actuality, it was negative. And this right here means that the model predicted that a value was negative, but it was actually positive. So in something like cancer classification, this is really, really important, because if your model is predicting that a bunch of tumors are benign when they are actually malignant, that's much worse than if your model is predicting that a bunch of tumors are malignant when actually they are benign. Because at that point, the worst that could happen is you maybe get an extra checkup versus having a tumor grow into a more cancerous tumor and then eventually kill you. So that's why printing your confusion matrix is important, because there are lives at stake, people. Okay, so going away from that, we are now going to talk about support vector machines. And support vector machines are hugely popular in classification problems. You can also use them for regression problems. In fact, all the algorithms that we're talking about from this point on, you can use for regression as well. But we're just going to use them for classification because that's generally what they are used for. So in support vector machines, what you're trying to do is the model is trying to group individual data points such that the distance between them is as far as possible. And this is a really cool concept, and the math behind this is pretty advanced. I'm not going to explain it now. As always, I'll have resources for you guys to look and learn on your own if you wish. But if not, you can just implement the algorithm in like 3 lines of Python, which is pretty awesome. So let's import, say from Scikit-Learn.svm, we're going to import svc, and then we're going to set our SVM for a support vector machine equal to svc, and then inside of here, we actually are not going to leave this empty. We are going to add a kernel, and that kernel is going to be equal to rbf. And this sort of goes in with the kernel trick, which of course I'll also leave resources for. But this is just a hyperparameter that we're going to be playing around with. Of course, you can do whatever you like. You can get rid of the kernel, whatever you want. But just for this example, we're going to be using a kernel just to show you that it works. And now if you wanted to make a support vector machine for something other than a classification problem, like a regression problem, instead of importing SVC for support vector classification, you would import SVR for support vector regression. That's important to note. Next, what we're going to do is we are going to call svm.fit, and we are going to fit our X train to our Y train. All right, so we'll run that bad boy, and you can see right here under kernel, it says RBF because we passed in kernel as being RBF. Sweet. So now it's time to print the confusion matrix. What we're going to do here is we're going to copy these values and we're going to paste them here. And instead of doing our logistic classifier.predict, we're going to say svm.predict, and that should be it. So we'll run that. And you can see right here we get the exact same result. Now, it's important to note that because our test data is pretty small, it's only about 100 entries, you're not going to see too much difference between these algorithms. But as the data sets that you're working with become more complex, have more features, more complex patterns between each other, and more importantly are larger, the types of algorithms that you're using are going to generate vastly different results. But overall, support vector machines do work better than logistic regression. Now, obviously, if the problem is really simple, it'd be easier just to use the logistic regression classifier because it's just, very simple, not going to take a lot of processing power. You don't want to reinvent the wheel and just make a super hard, elegant solution to a really simple problem. And with that being said, it's on to decision trees. And now decision trees are something that you've probably heard of or used or thought about outside of machine learning. And basically the idea is that you want to break up actions and features, and then at the bottom you'll have different classifications. So an example that's popping up on your screen is, let's say you want to make a decision tree for deciding if a person is fit or unfit. So you would say, okay, does that person eat a lot of fast food? Then if it's yes, then they're unfit. If it's no, then they are fit. Same thing with if they exercise regularly. If they exercise regularly, then they're fit. If not, they're unfit. So that's a very basic example. But a lot of companies use decision trees to map out more complex features and map out more complex trees of what a data set is trying to show when they're trying to classify new data points. And so that was a little bit of a wordy explanation, but hopefully you guys sort of get the general idea of what a decision tree is doing. And basically, in order to implement our decision tree, all we're going to say is from Scikit-Learn.tree, we're going to import our decision tree classifier. And as you've noticed, of course, we can also do decision tree regression, which isn't very common, but it does actually work surprisingly well, I found. Generally, at the bottom, you're going to want to have your classification, like it's this class, it's this class, it's this class, at the bottom of your decision tree, which is why we're going to be using decision trees for a classification example rather than a regression example. Okay, so now let's make our model. We'll call it tree, and tree will equal decision tree classifier, and our criterion will equal to entropy. So that means that our criteria will be focused on the entropy of the model. That's just a hyperparameter that we're going to be adjusting. Finally, we're going to call tree.fit, and we're going to fit the x train to the y train. All right, so we've run that. You can see right here that our criterion is equal to entropy, and now it's time to print out the confusion matrix. So I'm going to copy and paste the same code from above. Looks like I copied too much. And instead of ypreds doing svm.predict, it's going to be doing tree.predict. So we'll run that, and you see here this one decision tree is actually less accurate than our support vector machine and less accurate than our logistic regression example. And the reason for that is that one tree alone is not very strong. So if you think to those competitions that they have, well, they'll have a certain amount of items in a jar, and you have to predict how many items are in that jar. Something that's really interesting about human intuition is that each prediction will be pretty far off, but if you add up all those predictions and then divide them by the number of people who made those predictions, you'll find that you get a number that's very close to how many items are in that jar. And so that's something that's really cool about human intuition that also applies to machine learning. One tree is not going to be very strong, but if you have a forest of trees, then it's going to be a much stronger model. And that is the idea from random forest classification. And this is getting into what we would call ensemble learning. The idea behind ensemble learning is that you create a bunch of weak models, and then if you combine them together, you can make a really, really strong model. And that's what we're going to get to a little bit in the next video when we talk about optimization. But for now, we're just going to give you a taste of what's to come by creating a random forest. And basically a random forest is just a bunch of decision trees. You add up their predictions, divide them by the number of trees, and then you're going to get a more accurate prediction. So we'll say from sklearn.ensemble, we are going to import our random forest classifier. And remember, you can do a random forest regressor too if your problem is a regression problem. And we'll say forest equals random forest classifier. And our number of estimators, or number of trees, is going to be equal to, let's just start out with 100 trees. And our criterion will be equal to entropy. And it's important to note, decision trees are extremely powerful, but unlike some of the other algorithms, classification algorithms that we've worked with, they are prone to overfitting, which is why it's important that we have a test set so that we can make sure that our algorithm doesn't really understand our data set well, but not understand new data points. So we'll set criterion equal to entry, and we'll just say forest.fit, and we'll fit the X train to the Y train. We'll run that. Okay, everything looks Gucci. And now it's time to see if our random forest is any more accurate than our singular decision tree. So we'll run that. Instead of tree.predict, we'll say forest.predict. We'll run that. And you can see now instead of 5 incorrect predictions, we only have 4 incorrect predictions. So you can see that between each of these examples, the actual gained accuracy is rather marginal, and that has more to do with the data set and the size of the data set and the testing set than the actual algorithm. But you can see overall, our support vector machine performed the best, as well as our logistic regression classifier. However, our random forest did not perform as well for this particular problem. Some problems you'll find that the random forest works better. Generally, you're going to want to use a support vector machine. There are some problems with support vector machines, but overall support vector machine is probably the best classification algorithm that we've looked at, up until when we get to the next video, which is optimization. And with optimization, we're really going to dive in to ensemble learning, and we're going to see how powerful it can be, and also how quickly you can build a model with ensemble learning versus just doing something like deep learning. So yeah, guys, that's pretty much it for this video, and I will see you in the next one. Sweet. Thank you guys so much for making it to the end of this video. As always, if you enjoyed it, make sure to hit that like button. Also, if you have any questions, comments, or concerns about what we did in this video, please leave them down below. Now, if I could have just one more minute of your time, I would like to tell you about a service that I've been using for over a year now called Scribd. Now, just as a side note, Scribd did not sponsor me to make this video. I just wanted to tell you about it. Put simply, Scribd is a lot like Audible, except for instead of being $15 a month, it's only $9, and instead of only having 2 audiobooks per month, you get an unlimited access to a plethora of audiobooks, ebooks, documents, and even sheet music and magazines. So for me, this was obviously a no-brainer, and right now, if you use the link in the description, you get 60 days free of Scribd, and I get 1 month if you sign up using my link. So that's why Scribd didn't officially sponsor this video. I'm just telling you about it so that I can get some free months and I can continue learning, and you can also continue learning with your 60-day free trial. So thank you guys so much for making it to the end of this video, and I'll see you in the next one. Peace.